I'm very happy to have Yedid Hoshen here from Darwin University. So among many other prominent positions, Yedid was a research scientist at Facebook, AI research in New York and Tel Aviv. He completed his PhD in Darwin University. Before that, he studied physics at the University of Oxford. And his main research interests, where he also had many influential work, are deep learning, computer vision, and speech recognition.
Thank you very much.
Thank you.
So, thanks for having me. It's great to be back in Tel Aviv. So today I'm going to talk about the new research direction that I'm really excited about. I work on a bunch of other things like generative models and defect detection, anomaly detection, but this is something completely different that we're doing, and I'm excited about it because it raises a lot of interesting questions. So maybe some of us don't know this, but recently there's been explosive growth in the number of neural network models that are available online. So in Hugging Face, which is the probably the biggest neural network model repository today, there's more than 600,000 neural networks, and they're being uploaded at a rate which is higher than 2,000 models each day. So by the end of the year, there should be more than 1 million models available on Hugging Face. And there should probably be more other repositories. So basically, this begs the question of what do we do with all of these models? They're basically just being uploaded there, and the people who uploaded these models know what to do with them, and maybe some very popular models are being used by some other people, but most of these models are being completely unused, they are disorganized, we don't know what to do with them. And so we need to make sense of them in some way. Now, the way that we're going to do it is we're going to describe each model just by its weights, right? Because weights fully characterize each model. And so each model is generally characterized by its weights. We don't know anything else about these models. And we're going to find some way of organizing these models using weights. Now, because weights are very difficult to interpret, right? We don't have an easy way of understanding what a neural network does given its weights. This is going to be challenging, but we'll show how we tackle this. More generally, we see these neural network weights as a new data modality. Think about digital images 40 years ago, or audio, right? This data modality, you have a lot of examples of this data type, and you need to make sense of them in some way. There's all these tasks that you do on them, like registration, retrieval, clustering, anomaly detection, right? All of these classical questions, how do we do them on neural network models? But I think maybe more generally, we want to ask the question of what are the new problems that we have with large collections of neural networks that we didn't have for images, for audio? What are the new big questions? So in this work, we're going to tackle maybe one aspect. We take inspiration from Darwin's Tree of Life, where Darwin basically took the species, the biological living species that we see at the moment, and tried to organize them into a family tree, into a tree of life. Right at the very top, at the root, we have the oldest, most common ancestor, and at the roots, we have the species that we observe today, and obviously in the middle, we have more intermediate ancestors. Now, the challenge is to take the species that we observe today and infer this tree of life, which is not obvious. Now, Darwin mainly used the phenotype, which is the appearance or the behavior of these various animals. But more recently, now that we have genetic information, then we can reconstruct the tree of life from genetic things like DNA and omics and other things, other features like that. Okay, so the agenda for today has 3 parts. The first, we're going to introduce the model tree, which is the equivalent of the biological tree of life for neural networks. Then we'll define 2 tasks and propose ways of tackling them. The first one is recovering the model tree from just a collection of models, each one of them just characterized by its weights. And the second task is to predict the weights of the parent model given the weights of the children. I'll explain what this means when we get to it. By the way, my talk today, I think is timed at around 45 minutes, so we have time for questions. So if you have any questions, yes.
In this slide. So again, but what is the ultimate goal? I mean, even if you do that, why you get better understanding about what neural networks are all about?
Okay, so I get it.
Okay.
Okay, so just two slides about the background. I'm sure most of us are familiar with neural networks, so I'm just going to define my terms. So neural networks are obviously a very important class of parametric models. The model is fully specified by by its weights, which are just a bunch of matrices that characterize each layer. And they obviously have many interesting applications that we know about, language modeling, image categorization. Now, the most relevant aspect of this work is the fact that to find the particular combination of matrices of neural network weights that are optimal to our task, we do training, right? We choose these matrices that are most relevant to our task. And typically in training, we initialize these weights with random numbers, and then using the training set, we operate some sort of iterative algorithm like stochastic gradient descent, converging on some better solution for these values of weights, so that we can actually give them an image, we can categorize it properly. Now, another thing that is done in deep learning is fine-tuning, where instead of initializing these neural network weights with random numbers, we initialize them with the same matrices of another network. This is called fine-tuning as opposed to training, as opposed to pre-training. And this is actually quite important and definitely important for this talk. Now, the dominant paradigm at the moment, I would say, in the most of AI space.
The structure, in fine-tuning, the structure remains the same, or the structures of the bottom layers?
The structure remains mostly the same. Sometimes maybe the top layer, the final layer, and typically you would change the final classification layer, but most of the other layers change. It's stay the same. So maybe just a very.
This is today. So.
This is not today. This is not something new. Everyone does this.
No, but what I meant is that maybe in the future we can envision ways to initialize a neural network with the data with parameters of another neural network where the structure is different. Maybe smaller network using an orthogonal projection or some.
So these things are done to some extent already at the moment.
Well,
but the
adapters add to the network in order to fine-tune only small networks, like the LoRa.
Oh, so I'll get to LoRa, but LoRa is still initializing with the weights for the previous network and then doing some small adaptation.
Okay.
This is a big deal, but I think what I'm describing now is the most common thing that's being done, and there's a million different words extended. Now, the dominant paradigm at the moment in AI, I would say, is that we train large foundation models, something like GPT. We train very large models on very, very large general data sources, like GPT that's trained on the entire internet and some other things. And then for our specific task, where we don't have a lot of data, we fine-tune this model. We initialize our model with the weights of this foundation model, and then do a couple of iterations of stochastic gradient descent, usually stochastic gradient descent, to converge on weights which are specialized to our task. Now, the reason why people do it is because fine-tuning from foundation model weights generally achieves much, much better results than random initialization. Right, that's the only reason why. Okay, so that's pretty much the only background we need to this. Okay, so let's now define the model tree. We define the model tree as a structure where at the root we have the foundation model, the model that everything was fine-tuned from. And the children of each parent are the models that were directly fine-tuned with, which means we took the weights of the parent model, we used them for initialization, and then we continued training from that. We continued the optimization. Right, so these would be the children, and obviously these children may have other children and so on until we get to the root. Until we get to leaf. The leaf model is a model that nothing was fine-tuned for. Okay, so this defines our model tree. Now, I just make sure all nodes, all models have a single parent, apart from the group that doesn't have, right? But models just have a single. Models can, of course, have many children. Now, in model repositories such as Hugging Face, there are multiple foundation models. So indeed, characterizing them as a tree is not quite the correct structure. The correct thing is a model graph, right? A model graph is just a set of model trees. Each tree starts from a foundation model, and the trees continues from there. And we have a couple of foundation models, each one of them spanning a tree, and the collection of all of these trees is the model graph. Now, of course, we can have trivial trees just consisting of a single one. But hopefully we don't have too many of those because we can make many of these things that I'm talking about.
Forest, right? Like a forest.
Yeah, we prefer the forest. We prefer the graph, but the forest is a more accurate. Right?
There's no cycles, right? Then you're not
Yeah.
gonna.
There are no cycles, and there are also no like two parents.
Yeah.
Bringing like one child, which is quite common in biology, but we don't have that. I'm not saying that's impossible to do for deep neural networks either, but we're not modeling. Okay, so these were all the definitions, and now we can get to the actual task, which is given a set of model checkpoints, just a set of models, each one of them characterized by its weight matrices. We want to output the model tree or graph structure of this set of models. Right, and this work is by my students Eliyahu Horowitz and Asad Shul, and it's currently an archive and was exhibitions. Okay, so here we're obviously using something which is quite similar to using genotype in biology. We're using the genetics of these models, we're just using the weights. We're not looking at phenotype, we're not looking at how they behave. We're not going to insert data into them and see what these models do. We're just going to use the model weights. What are the advantages? The advantages are that, of course, weights fully specify the model, so that's a good start. But the other practical advantages are that we don't need to have access to data for this. We just need to have the model weights, and that's it. We don't need to know what data is trained on. We don't need to have the ability to run the models. We don't need to have the ability to train them. We just take weights and get these graph structures from them. Why do we care about this? Well, the most obvious application of this is ownership verification. I have two models, right? One of them, its owner claims that the other model fine-tuned from them, and so they have intellectual rights over the other. The other person makes the opposite claim. What's right? How do we know? Right? So obvious how we do it. But if we had the graph structure, we would have known which one came first and which one took. So we could have interesting legal applications. Another benefit is imputing metadata between models. Right? We know in computer science that when we have a graph structure, we can impute information between neighboring nodes. Right? So once we have this tree structure, now it's also quite common in Hugging Face, but some models have a lot of metadata, how they were trained, what data set, what function, etc. And some models have none. So if we knew the tree structure, the graph structure more generally, we would be able to impute information between these various models. Right? So graph structure gives us a lot of power when we have. And finally, as maybe a slightly more vague and less defined goal, we want to be some sort of Google model weights as a way of, we want to be able to have a user that looks for a particular model, and then given maybe metadata that we have for some models and the graph structure that we have for these models, we will be able to retrieve the model that's most similar to the user's needs. Maybe the user would also need some fine-tuning or something. Okay, so having this graph structure is typically quite important for search or imputing information, and also gives us ideas of ownership verification and understanding of this. So, inferring the tree of life just for model weights basically requires solving two tasks. The first one is to be able to understand if there exists an edge between the models. That's to say, if they have a fine-tuning relationship between them. The second task is inferring the direction of time. Which one came first, which one came second. At least in our approach, these two questions have different answers. Because usually distances don't tell you which direction the relationship goes, whereas if you need something else to tell you about directionality. Okay, so let's start from our first observation. We found that by looking at the distances between the weight matrices of different models, we can infer how far they live on the model tree. So you can, for start, you can think of just taking the Euclidean distance between the weight matrices and doing that for every layer in the network. And this gives you a general distance between these models. Now, we found that this particular thing doesn't work that well, but what worked much better is taking the maximal value. We compare all the weights between these models, and we find the weight that changed the most. And this value can change, the maximal change in weights between these models is what we take in the model distance. It's basically the outlier distance between all of these various weights. And we found that this number characterizes the distance between models to the highest accuracy. What do I mean by accuracy? So we created a data set where we know the ground truth on the model tree, how far we compute the minimal distance between models on the ground truth family tree that we have. And we compute the correlation between the distances between the weights of the models and the ground truth distances on the tree. And we found that the correlation between them is close to 1. So that's how we define this distance.
So yes, you have it like a tree or like a forest that you know its structure, and then you compare different weights to the tree that you know. Like you have like no labels, and then you compare the different weights compared to the labels, right?
That's what we evaluate.
It's valid. Okay.
Yeah. So
but maybe I don't know, a different method would be to compare it to its functioning. Maybe a lot of distance comes from parts of the weight that therefore has no effect on the functionality of the tree of the model. So I mean the several different ways to decide what is the right measure, right? Similar to genetics.
Right. So I agree this metric is quite simple and is naive in the sense that it looks at the raw weights as opposed to some semantic representation of these weights, which might have been a clever way of doing it, and it might have been more effective, but we don't know how to do it. It's probably a better way of doing it, and we are thinking about it, but we don't have a good solution yet. And we found that this works nicely on the model tree actually.
And so you also try to find how good it's correlated to the functioning, to the semantic.
So we're assuming that the distance on the model tree is also quite related to the semantic similarity between these models, because basically each step on this model tree means that I went through another step fine-tuning. So I'm assuming that it should be correlated, but we don't have a very easy way of measuring it, because once you get into semantic things, you need to define what your semantic knowledge is and what distance. So we didn't do it yet, but it's definitely a promising direction that we're thinking about, but we don't have anything yet.
Okay, so if you have a weight of 1 million parameters, take the only scalar that differs the most.
1 million parameters isn't too many. We have more. And
Yeah,
yes,
but the
yes, we
single-
do exactly.
If only one number in those 2 parameters, that's your.
Yeah, I think we
This
did
is-
that also for billion. Yes, and we just took the single number and it worked the best across all layers, across all matrices, and it worked the best. Now I'm not saying this is the optimal thing to do. I'm just saying this is the best thing that we found.
With us in the data set that you used to check this correlation, did you have various ways of fine tuning? So like, if you also include the less layer, and in some of the fine tunings, the less layer was simply removed or completely changed, and this will will affect this distance, and there's a difference if I just fine tune the last term or I try to fine tune the entire model.
So I think there's two parts to the answer to this. The first one is that if there's the major changes between these models, then you just want to ignore these layers.
Yeah. So we did ignore this layers for the
And we ignore the final layer.
the final. Oh,
So we ignore. So we didn't do anything because Chico does not ignoring it. But in terms of like the algorithm of these models, so they worked fine. And we did that over quite a few different models. Like you see what we experimented on. So it seems to hold quite generally. But again, experimentation could be a lot more extensive, and I'm sure there's a lot of corner cases that we know about. So I think we just going. This is just the first step. But I think once we drill into it a lot more and try to analyze a lot of different scenarios, we'll see that this measure is very neat. But as the first step, I think it works fine. Sure.
You said you tried the Euclidean distance. Guess this is kind of like the infinity norm.
Yes.
Have you tried anything in between? So it's kind of maybe more robust to
Singular values.
yeah, like L3 norm, right? Something like this.
Did we try higher moments? We didn't. Your intuition makes sense to me. I think we didn't. I think we tried a bunch more things. I don't remember them exactly. I think we tried looking at maybe percentages and saying, let's look at the top 20% or something like that. And then do the Euclidean distance on the top 20%. I think we tried that and it would work better than the maximum, but we didn't do it very extensively and very systematically. So I would say that I'm pretty certain there's something better than what we did, but it worked okay, and I'm sure there's something. Okay, so that was the question of how far away different models are on the model tree. Now we need to determine directionality. So for that, we found something that we thought was surprising. We found that kurtosis is very relevant for determining directionality. So just as a recap, what's kurtosis? We take each weight matrix, we basically flatten it, we treat it as like a set of scalars, and we compute its mean and standard deviation, we subtract the mean, we divide by the standard deviation, so that now we have a variable with mean 0 and standard deviation 1. And now we compute the fourth moment of this distribution. But this is kurtosis. This is the standard deviation of kurtosis. So that's nothing surprising. It's just statistics. Now, the surprising thing was that when one monitors, and when we have multiple layers, we just average. Okay? So we compute it for every layer. So this would be the kurtosis of the model. Now, the surprising thing that when you monitor kurtosis throughout training, you find that during generalization, which roughly corresponds to pre-training, I'll define it more clearly in a second, and kurtosis increases. And then during specialization, which roughly corresponds to fine-tuning, kurtosis decreases monotonically. You can see the graphs over here. There are different checkpoints through time in generalization. This is different checkpoints through time in specialization. And you can see reasonably monotonic behavior. And it's not, I don't think there's any cherry picking, right? It actually behaves like that. And the cherry picking maybe is the fact that it doesn't happen for all layers. Attention layers don't exactly behave like that. It only works for dense layers. Okay, so just before I try to give some intuition for why I think this is, when I mean generalization, I mean that the model starts with weights that don't know so much, that maybe are randomly initialized or initialized with a weak model. And then we continue the training on a more general, more complex data set. In specialization, it's the other way. We start with weights of a model that is that knows a lot, that was trained on a very large data set, and we specialize it to a very specific data set. Okay? So what's the intuition? The intuition, at least for me, we didn't prove anything, but the intuition is that the more that basically when we want the model to become more expressive, to know more, then the weights need to take more outlier values. And kurtosis roughly corresponds to how heavy or how thin the tails are, right? So it basically tells us how many outliers we have in distribution. So when we want the model to be more expressive, we basically we need to increase kurtosis. When we want the model to become more specialized, so in effect less expressive, kurtosis increases because it needs to become less expressive.
Yeah, is that what's the mean there? The kurtosis formula?
What's the mean?
Mean is the mean.
Right, because this is the entire formula, including both the standard deviations and the averages, just in one formula. I basically broke it.
So this is the mean over all matrices?
This is we do it for every matrix individually. Sorry, yeah, this isn't very good notation. It should be mean over layer number. This it looks like a mean over everything, but it's a mean over just the particular matrix. Yes, please.
Can you please elaborate what are we seeing in graphs?
Okay, so in these graphs, we basically we trained the model on some data set, and we took various checkpoints of this model, and we computed the kurtosis to this checkpoint. And this is basically the kurtosis as a function of the training step, and you can see that it monotonically here it increases in generalization. Here, when we did fine tuning, you can see that it monotonically increases. Actually, as a party trick, if you want to take a set of unordered checkpoints and order them, just compute kurtosis, sort by kurtosis, and it orders them through. Just
the y-axis is the same in both graphs, but once it's negative, once it's positive.
And these are not the same models. So the y-axis is the same in both graphs, but these are not the same models. And also, you can see that kurtosis can't actually be negative.
Yeah,
so why is this negative?
Why?
Because they usually do -3 in kurtosis computation because a Gaussian has kurtosis.
Okay.
Yeah, sorry, that's good.
So during the fine tuning, the specialization stage, you trained on a different subset of the data set for pre-training.
We function in a different data set. Yes.
So if I take this magnitude, we have to say that the increase in generalization is much larger than the decrease in fine tuning, at least the numbers suggest.
So in these two pairs of models, I definitely agree. Whether they hold more generally, I don't know. I don't know. I need to check. So it's an interesting question that we have not.
These teachers took like 1,000 models from Hugging Face, and you check the order. And you see this behavior across all models that you observe.
So we didn't do it over all the models in the Hugging Face, but I'll show how we experimentally verify. This is, I guess, more minor verification on a couple of models that we trained ourselves. And in a second, you'll see how we actually verify this. Okay, so let's just show a simple algorithm for giving the family tree of 3 models. So we have 3 models, we just know the weights, we know nothing about them. So first, we compute the distance, the weight distances between these models. As we said, the maximum of the distance between layers, and it gives us a number for the distances between each pair of models. But because we know the linear tree, we know there are 2 edges and the third one is missing, so we just drop the edge with the longest distance. So the 2 nodes that are that have the longest distance, we just drop here. But we know nothing about directionality, right? It could be that A is invisible, it could be B, it could be C without. And now we use kurtosis. We assume this is in the specialization stage, which is a limitation to our method, because we need to know whether we're in specialization or generalization. And it kind of goes against the story that we know nothing about the models. This is a limitation of the method. We're trying to solve it without our solution. So we compute kurtosis for each one of the models. And then we take, assuming we're in specialization, the root has the highest kurtosis. So we designate it as the root. And then it gives us all the directionality. So assuming A is a root, then we know that B function of A is function of B. If B is a root, we know that both A and C function of B, and so on. Okay, so this is a simple algorithm when we only have 3 models, right? And it's more of an illustration of how these 2 measures help us compute the family. Now, of course, we can generalize it to LLM, of course, but we can generalize it to an arbitrary number of models. The way that we do it is we compute a cost for every directed edge. And it's basically just a linear combination of the weight distance between these two models. Right, then edge sets between two models, we compute the weight distance between them. This is this Bij, and three models Ij. And the sign of the kurtosis change. Assuming that we're in specialization, then I want kurtosis to decrease every time I go down the generation. And so if kurtosis increases, there should be some cost associated with it. Note that I'm not using the magnitude of the kurtosis change, but just the sign, which I think goes back to Yeshai's question, because the magnitudes are not. We didn't find that they were very meaningful. We found the sign to be more meaningful than the magnitude. We just don't understand. Okay, so this gives us the direct spot between the two edges, because obviously the order between I and J makes sense. Example, he doesn't have. It's a hyperparameter which shows something. We did a lot of fine tuning on it and it just worked. There's probably something clever to be said about it, but we don't.
So say if I have some foundation models and then I fine tune it, then this kurtosis is going to decrease. If I have a model that was fine tuned to, like I have foundation model for voice audio, then I fine tune it to one task. Then instead of taking the foundation model, for some reason I take this fine tuned model, but do it for a different, completely different task on audio. In this case, will it the kurtosis still
I think
increase?
I think because in our data set, like the children were generated like that, and kurtosis didn't.
On completely different tasks. So maybe I have
So
word detection, then I have emotion recognition or something.
So I think it's a good question how far away like this goes. Like maybe there's some point at which it won't decrease. I don't know that. But so far we found that fine-tuning things actually decrease kurtosis. But I'm sure there's some extreme cases or some interesting cases where this doesn't happen. We didn't use that, They assume that it decreases, but I'm sure there's more research to do. Okay, fine. So now we have the cost between the directed cost between every pair of edges. So now we realize that what we're looking for is just the minimum directed spanning tree. Right? Because we're looking for a tree, it's directed, we want to minimize the cost, so this is the minimum directed spanning tree. And once we realize this trick, which I told you that it's not a new trick, they're already using it in computational evolutionary biology. Then we already have very well established algorithms for doing this. So we used an algorithm which is called the Edwards algorithm, which has complexity of the order of the number of edges and the number of virtues, which in our case is the number of models squared. That's the back. But there are faster algorithms. It just doesn't matter in this case because the main cost is actually computing the pairwise distances between models, because these models are huge. So computing this distances between these models is really expensive. That's the main the algorithm, not these graphics. Okay. So I just left out one thing, which is how do I actually infer the model of a graph, right? Because here I assume that everything lies in a tree, but things don't lie on trees, they lie on a set of trees. So what do I do about that? So the idea is that I get a set of models, I cluster them because I have a distance measured between every pair of models, so I can use any clustering algorithm, specifically we use k-means. So we first cluster them into a number of sets, and then these sets we run our we compute the tree using the algorithm the previous slide, and that's it, right? Then this gives us the model graph, right? Then you could of course ask, how do I know what's k? I don't like everything in k means I don't know anything.
So in bioinformatics, there are two approaches. Parsimony approach, it's very similar to what you're doing when you're trying to. And then there's the maximum likelihood approach, which tries to ask probabilistic models. So is that kind of being relevant here to consider a probabilistic maximum likelihood approach to generate that?
I think it's relevant. We didn't do it. We haven't. I guess we would need to define like the pairwise probabilities for the changes, and we don't know how to do that yet. But I'm sure with more research, and I know that the most recent approaches in bioinformatics they prefer the maximum likelihood of best intelligence. So I think this could be an interesting follow-up. Just be able. Okay, so let's see some results. We created a data set by taking various vision transformers, starting from 5 foundation models, reasonably famous models like, MAE, Dino, but we took fairly big important foundation models. And for each one of them, we fine-tuned it on 4 data sets, and then each one of the children we fine-tuned on 4 other data sets. So altogether, we have more than 100 models in the data set we created. Spanning 3 generations and 5 different trees. And then we ran our entire network on this, and we achieved an estimation accuracy of about 89%. It's not perfect, but it's way, way better than that. Okay, so on this synthetic data set that we created, it's not that synthetic, but it's somewhat synthetic. It seems to work nicely, not perfectly, but nicely. I think it's more interesting to see how this works on real models that other people train. So we took the Llama family of models. Llama is a model family from Facebook AI. They first trained Llama 2, and then they have a bunch of children from it, like one for chat, and one for code, and another one for Python, and so on. And they even have like cell generation. So we have these 5 models. We assume that we don't know anything about them, and then we ask our method, please give me the family tree for these models. And we've actually been able to predict them perfectly to this. And how do we know how Meta actually trained these models? In the paper, they actually gave the family tree. So we actually have a ground tree. This is rare. They usually don't give the family tree. Here they do. Okay, another real sort of family of models that we tried is the Stable Diffusion family. Stable Diffusion is a very famous text-to-image model used quite a lot by the Gen AI community. And at least the earlier model was numbered from 1.1 to 1.5. They all had just about the same architecture. But they were interesting because 1.1 basically was trained on the smallest and least interesting data set. And as they increased, as the numbers increased, they basically trained on larger and more steady space. So this is all actually in the generalization stage, right? Because every model, although these models were fine-tuned from each other, they were fine-tuned to become more precise, not less precise. And so when we took these models and we created the family tree, we predicted the following intelligence. We basically predicted that they were all sequentially predicted from each other. Now, the metadata on these models is a little bit asynchronous. It seems as if they're claiming that both 1.3 and 1.4 were fine-tuned to 1.2, which is not predicted. We predicted 1.4 was predicted to 1.3 was fine-tuned to 1.3. But the metadata is so casey that we don't even know what we're doing. So at worst, we're wrong on 1%, but we got the other one. Okay, so this seems to work on real data.
According to the intuition, the directionality of the graph should be reversed because we perform generalization and we extended that instead of
Yeah, so we flip the sign of the hypothesis as we should. Okay, just to see that kurtosis is special, we looked at various other statistics apart from kurtosis and we fine-tuned 5 different models and we looked at various statistics, and we can see that only kurtosis increases monotonically as a function of training. The mean doesn't. That's strange things. Variance sometimes increases. Skewness sometimes increases. Sometimes speed increases. Even entropy of the weight sometimes increases. Sometimes decreases. And for some reason, kurtosis is special. We don't know that. We don't understand why kurtosis is more special than entropy. That's something we're thinking about. We're trying to understand.
Curious, how did you come across this layer? Just just brute forcing, let's just try different moments, or you had some.
So it's actually my second guess.
So I think I have some intuition, like the
Yeah, the intuition is actually the thing that that we described. The fact about generalization and the fact that we need more outliers to make this. But it doesn't explain why ketosis makes more sense than variance. So because that we regularize when we do LT regularization, we regularize the magnitude of the weights, which actually correspond more closely to variance. So variance was for the first place. Didn't work, so tried to versus. So it was a second guess, not so much brute force, but again, I still find it somewhat difficult to explain why ketosis works and variance doesn't. Also, it works on the dead layers and doesn't work on the attention layers. Why the attention layers don't behave like that, I don't know.
How sensitive do you think it is to the type of fine-tuning algorithms that are used, like someone changes in a year those algorithms, maybe ketosis no longer looks so good.
I don't know for sure, but I know that we've tried on various model families that use different fine tuning and it worked. So from that perspective, it seems fine. But I don't know when people want to use SGD, then use some completely other optimization algorithm, maybe things will behave differently or different regularization to the weights. I don't know for sure, but I know that currently for various model families, it seems to work fine. We need to understand this better. Okay, so actually I have less time than I could do. But let's describe another task that we worked on. This is somewhat more challenging than the task of reconstructing the family tree. If you think about the biological anomaly, in the analogy, imagine that you have the DNA of snakes and lizards. Can we recover the DNA of the dinosaur? Right? Or more specifically in our case, given a set of weights of children, can we recover the weights of the parents, the animal? And we call this task pre-fine-tuning weight recovery. This is work by my students, Eliyahu Horowitz and Jonathan Kahana, and we'll present this in ICML. Okay, so more concretely, we treat, in this task, we treat every layer individually. There's no loss of generality. You can look at each layer in which we have this fine. So for each one of the children, we have a weight matrix, which we denote W tag defined, right? And we want to recover the weight matrix of the parent model, which we denote by W. Now, we assume no access to data or ability to run it. Why do we care about this? Well, so one motivation is that generally when we train foundation models, we train them on a lot of unsafe data. Like for example, we train large language model on the entire internet, and we can say things and give bad advice and things like that. So we never actually release this model. What we do is we take this model and we fine-tune it on safe data. This creates safe child, and these safe children are the things that we actually use. Okay, and because training these foundation models is so expensive, we usually train multiple children of this unsafe parent. Okay, so if given these children, we could recover the unsafe parent, then this is something we should know about because we do safety training for this. Okay, so I just give a little bit of background necessary for what we do here. So generally when we fine-tune a large foundation model, it's really, really expensive because these models have many, many parameters. And so this is both parameter inefficient and very simple. The idea behind low rank adaptation, or LoRa for short, was to keep the weights of the parent as they are and learn an additional weight matrix, which we denote by M. And this matrix is low rank. So because low rank matrices are easily parameterized using very, very, very efficiently, we just fine-tune this additional adaptation matrix M, which is low rank, so very simple. And we don't touch the original weights down. Right, so this can be parameterized in a very efficient way because the low rank matrix is much smaller, or at least it's the product of two small matrices. Now, this is a very, very popular way of doing fine tuning, and I would say that most of these 1 million models use LoRa for fine tuning also very. Okay, the reason why I motivated using LoRa is that we assume that the children will fine tune using LoRa. So our method is called spectral tuning. It tackles this task of recovering the parent with children, and we assume two things. We assume that we have multiple children, and we assume that fine tuning uses LoRa. Now, the main trick here is that the weights of every child, which are observed, right? These are the models that we actually see, which we know that we can give a constraint on the weights of the parent W. Why? Because we know that W tag equals W plus the adaptation matrix N, which is LoRa. So each one of these observed children gives us a constraint on the unknown parent W and the unknown adaptation matrix Ni. Right, so it's the same parent for all of the children, but the Ni changes between these various children. The interesting thing though is that Mi is low rank, so this doesn't give us too many unknowns. Right, so each one of these children gives us a constraint like this, but because Mi is low rank, when we try to recover both W and these various Mi's, because these Mi's are low rank, every child gives us more constraints than new unknowns. Right, this doesn't have to be true. Two children may have exactly the same weights and then they won't give us any new constraints, but this never actually happens. Okay, so every child gives us a constraint and we want to recover the unknown parent weights and the unknown adaptation matrix, which is specific to this child. So this is an optimization problem, a constraint optimization problem, right? Because we have a rank constraint on Mi's and W is shared between all of these.
Do you know how?
So I have a slide at the very end where I show how to, but we can recover it pretty.
It will not be the same for each model.
It doesn't have to be the same for models, and we can recover it in a principle. But we didn't do it in the original version, then reviews asked for it, and we found the solution. Okay, so we solved this using alternating minimization. I'll give some intuition for this. This is actually a bit of a textbook solution, but I'll give some intuition. So first we did the W step, which means that we fixed the current solution to the adaptation matrices N1 to N, and we just want to estimate the weights of the parent W. So each child is given by W times I equals W plus Mi. So if we just change the sides of the equation, each child gives us an estimation of W, which is W times I minus Mi. Okay, so each child gives us an estimate, and we have estimates from all the children, so we just take the average, and this gives us an estimate of the parent given the weights of the children, and fixing the solution for the various steps.
Why not just gradient descent? So when using gradient descent.
It works much better for things. Okay, so now that we have some guess for W, we can fix W and try to solve for the various Mi's. So you can see from the equation that once W is fixed, then there is no connection between these various terms, right? So we can optimize each term individually. There's nothing connecting the various I's. And so at this point, for this, there's an actual textbook solution. The intuition that I can give for this is that, again, we solve for Mi, which is W times I minus W. But we also have the rank constraint that we ignore. So the idea is that we do SVD, we take the top R components, and this gives us the best of this M. Okay, so we have the W step, the M step, and we iterate on this until convergence. It takes about 100 iterations. On a CPU cluster, it takes about 3 minutes. So it's pretty fast. Okay, one more thing. If we do iterative optimization, we need to have some initialization. So because I don't have much time, the way that we initialize it is we just average all the children, right? We average the weights of the children, and this gives us a reasonable initialization. This is really easy to implement. It takes about 8 lines of code, of Python code. I won't go through these lines, they're in the paper, but it's 8 lines and they do exactly what they should mathematically. So it's really as simple as I said. There's two more tricks that are pretty simple. I'm not going through them. They would add maybe 3 or 4 more lines. Okay, now getting to the question of how we estimate the rank of the children without knowing them in the first place. So I won't go through exactly how we write a linear program, but the idea is that if you take the difference between 2 child weight matrices, then the difference between them is just the difference between the 2 allocation matrices. And the rank of the difference between 2 low rank weight matrices is upper bounded by the sum of the ranks of these matrices. So we have this constraint. And when we formulate this as a linear program, we eventually we can solve this and get good estimates for these ranks. And in fact, this typically recovers the rank stuff. Okay, so
Can you automatically get integer solutions?
yes. Okay. So how does this work? Here I'm showing the results for various weights in a single layer, in a single network recovered. Each one of those basically tells me how many layers have this accuracy. So initially, the children, if you look at root mean squared errors between the weights of the children and the weights of the parents, the differences were at the order of 10 to the minus 7 on average. And then after we recover the weights of the parents, the error between our predicted solution and the actual weights of the parents are something to the order of 10 to the minus 19 or 10 to the minus 18. Okay, so just by numerical averages. So this method recovers the weight of the parents just about perfectly. We have some outlier layers that we don't recover quite as accurately, but it doesn't change functionality.
You check the perplexity as well on the recovered parent model, you have to run it.
Yes.
with-
Yeah,
So you said that 4 children is enough to recover the parent?
4 is the minimum. Yeah, 4 would be the minimum. I have a slide on this, and I won't have much time for it, but I have a slide on this. So just if we want to understand what semantic results look like. This is the original model. This is stable diffusion. Takes a text prompt and some random noise and gives us an image. Now we fix the noises, and we take one of the child models and we show its results. So it's the same noise, the same sentence as this image, and you can see that they're quite different, right? They're not the same. Now, if you just take our initialization of averaging between all the child models, you get these results, which are pretty similar to the child, and they're not very similar. If you run our procedure to the end, and you take our predicted weight matrices of the current model, you recover this, which is clearly indistinguishable from them. So functionally, we recover precisely the current model. Here we have ellipse, which is also an low version of this functional similarity, and you can see that it's virtually perfect. We did the same thing for language models. Here's just a qualitative result, but we also did it numerically. I'm not going to go through it. It's boring because we actually recovered it perfectly, and the child models are very different, and we recovered the parent model perfectly. So how many children do we actually need for precise recovery? It depends on the model. So we've actually managed to get it down to about 4 children to get near perfect recovery. But for language models, it needed more. We saw that it needed maybe as many as we could. We don't have a great way of quantifying how many children we will need to recover the weights. And because we don't know the ground truth, we don't know if we got the right thing. So this is something that we need to do better. Okay, so just to recap. The tree of life enables organizing the known universe. And so we found a way of constructing a model graph using the weight distances and the totals. And it has applications in ownership verification, in knowledge imputation, and in search. Now, we've also found another way of predicting the weight of a parent given children. And this may have implications to safety in models. Now, I think looking forward, there's a lot of different questions that come with this. For example, we have, I think we came up with many of these questions, right? Are there better measures for determining if there is an edge between the nodes and the directionality? Can we use other ideas from evolutionary biology, from bioinformatics, and we organize some of these ideas? What else can we do with real life? Are there any good applications? And generally, when we have this population of models, can we do registration? Are there ideas for retrieval? Can we do anomaly detection? So I think this new playground is really exciting, and I think we're just starting out. And I think it will be, we're definitely going to continue working on it, and I think it's a great direction to be in. So thank you very much.